The other important direction that we can go with the data description is measures of variation. Remember, the mean, median, and mode are measures of central tendency. Central tendency means where does this data tend to lie, whereas variation is how far is it spread out. Well, the first of those is the range. It's simply the highest value minus the smallest value. So looking at our, another example, starting salaries of 10 executives, we have, in thousands, I didn't put that, we have 41,000, 38, 39, 45, and so on. And putting that into order, our lowest value is 37, our highest is 47, and so the range is simply 47 minus 37, which would be 10. So the range is simply how far is it spread, which is the highest value, minus the lowest value. So all of these so far are pretty easy. You've dealt with mean, median, and mode since you probably were in 7th grade. The range is real straightforward. You just subtract two numbers. But now we move into the things that are much more Shanita, I'm confused on median. If it is odd, does it mean it is just one number? The median is always just one number. So this, in this case, it's even, so we'll average the two middles. But let's say there had been 11 values, and in between here there was another number like, there was another number in between. Yes, it would be just that middle number. So if I were able to split this and have a center number, that would be the median. So I'm going to type that. If there was a center number with an odd number of data values, the median would be that center number. Okay, does that make sense? Okay, good. All right. Now, deviation is the difference between a certain data value and the mean. So first, you would have to determine a mean for your set of data. So for the starting salaries that I had up here a minute ago, the sum of all those values was 415. Divide that by the 10 values that there were, gives us a mean of 41.5. So add them all up, divide by however many there are, would be 41.5. And then the deviation for each data entry would be take that individual value minus the mean, gives a deviation, in this case of negative 0.5, because the mean is more than that particular data value. So 41 minus 41.5 is a negative number. The next value was 38. 38 minus 41.5 is a negative again, negative 3.5, and so on. You go down the whole list and you find the deviations from the mean. Now, an interesting thing that happens, if you were to add up all of these deviations, which is indicated by this expression right here, the sum of x minus the mean. So x is my individual data value, minus the mean is the average. And if I add up all those values, it always comes out to 0. And the reason for that is this mean is essentially right the center of the data. So if I figure out how far everything is spread from the center, some will be positive, some will be negative, but they always cancel each other out exactly. So long as you've rounded, you've left enough data accuracy, okay, if you're dealing with decimals. Well, so it became important to people to know, well, how much is this data spread out, and how could I make a measurement that could just tell me in one number how spread out this information was. the first thing they thought of was, we'll add up all the deviations, but if it's always going to come out to the same value, if your sum of your deviations is always 0, that's not terribly helpful. So somebody got the bright idea a pretty long time ago to manipulate the formula to obtain an overall average deviation. And the way they manipulated the formula was to square each deviation to eliminate the negatives, because you know that a negative squared is positive and a positive squared is positive. So now if you add up all the squares, you get a picture of the total deviation. It's bigger than it would have been because you squared everything, but we'll take care of that in a few minutes. So back to our chart. If I find all my deviations and take each one and square it, see how my negative deviations turned to positive and my positive deviations stayed positive? So now if I add them all together, I'll get a pretty big number. In this case, the sum of all my x minus the mean squareds is 88.5. Now, if I were to divide that by the sum of however many I have, can you see how that's an average kind of a formula? I have added them all up and divided by however many there are. So this is an average or standardized deviation. So now to get back to the original units, so we're not dealing in numbers bigger than they started, we take a square root. Because we squared it, we're kind of undoing that. Take a square root at the end. So here is the formula for standard deviation. It is the square root of the sum of, parentheses, each individual x value minus the mean, and then square it. And you divide that by n, which is the total number of data values. So in our case, that total was 88.5 divided by 10 was 8.85. I didn't do the intermediate. So now I have a square root of 8.85, which is 2.97489. And then that you would round to the required number of digits. So this formula is for a population. If they tell you or ask you to find the population standard deviation, then you'll use this formula. Sometimes they want you to find a standard deviation of a sample. So a sample is a smaller part of that overall population. So we adjust by dividing by n minus 1 rather than n. So the little n indicates the sample size, whereas the capital N represents the population size. It actually is more common for us to be working with a sample than with the population.